Hello and welcome to the Open Systems Media embedded tutorial, Learn to run two wireless protocols concurrently with one device, sponsored by Texas Instruments. My name is Rich Nass and I am the Executive Vice President of Open Systems Media. I lead the embedded and IoT teams for embedded computing design. If you are not familiar with that property, you will find it is a great resource for anything related to the design of embedded system, whether that's hardware, software, or anything in between. You can find it at embeddedcomputing.com. I will be your moderator for this session today, where you'll be hearing from Ryan Brown, an applications engineer for Texas Instruments, who is currently focused on connectivity software. He's held this position for the past 3 years, managing online engineering support and direct customer business opportunities. His work typically centers around 802.15.4 based technologies like Zigbee and Thread, but also includes TI's Dynamic Multi-Protocol Management, or DMM solution, to support concurrent stack operations. Let me talk briefly about the topic today and what you can expect to learn from Ryan. We are seeing more and more devices connected. I mean, that's an obvious statement. It might mean it's Bluetooth. It might mean it's Zigbee. It might mean it's something else. In the past, these connections were generally done discreetly. You would have had a Bluetooth connection with a Bluetooth transceiver, a Zigbee connection with a Zigbee transceiver, and so on. And that gets pretty clunky pretty quickly, especially when you're operating in the same frequency band. But we are here to help. Actually, Ryan is here to help. Before Ryan comes out, let me go over the housekeeping stuff. His presentation will take about 20 minutes. You'll find on your console window a maximize button that allows you to see the slides in a larger window. And there's a widgets button where you can download a copy of Ryan's presentation. Okay, enough from me. Let me bring out Ryan. All yours, Ryan. Take it away.
Thank you for that introduction, Rich. And thank you, audience, for your interest in this topic. I'm really excited to be able to share with you guys my interest and expertise regarding dynamic multi-protocol management using TI SimpleLink products. So let's go ahead and dive into it. So this session is called Learn to Run Two Wireless Protocols Concurrently with One Device. And this is achieved using the Dynamic Multi-Protocol Management solution on TI SimpleLink devices. So what is the Dynamic Multi-Protocol Manager, or DMM for short? Well, with the SimpleLink wireless MCU platform from Texas Instruments, multi-protocol solutions can be supported with a single chip using the Dynamic Multi-Protocol Manager software module. This allows for innovative solutions. For example, combining a Bluetooth low energy connection with a sub 1 gigahertz network. Therefore, you're able to commission and control the network through a Bluetooth low energy, but communication is accomplished over sub 1 gigahertz network. We'll go through several examples later on to demonstrate how this is accomplished. The goals of this session will be learning the basics of DMM through exploring common use cases, understanding how multiple RF protocols are going to be able to add value to your product, discovering the optimal wireless SimpleLink MCU for your application, and getting a quick overview of the entire SimpleLink wireless MCU family with recently introduced devices as well. At the end, you will receive the full resources necessary to jumpstart with development. Let's go ahead and get started. So a high-level overview of the multi-protocol manager is as such. It starts off with two stacks. You have stack A, let's say BLE, Bluetooth Low Energy, and stack B, let's say proprietary sub 1 gigahertz. And these two stacks both have an application and the underlying stack that are attempting to communicate to the radio driver. With introduction of the Dynamic Multi-Protocol Manager, we have a DMM Policy Manager, and each stack application is going to be reporting their stack states to the DMM Policy Manager, which is then going to create a priority schedule that is going to correspond to the radio driver. That way, the radio driver knows which stack should hold priority and communicate over the single dual-band radio at any given time. This is going to allow for the stacks to share the single radio driver resource and be able to communicate both of their needs based on their priorities. This technology, the software module that is DMM, supports all of the stacks available by Texas Instruments. This includes Bluetooth Low Energy, Zigbee, sub-1 GHz proprietary solutions, TI 15.4 stack, both at sub-1 and 2.4 GHz, and Thread. So let's walk through a user application of DMM. First, you have a single stack changing its application state. It's going to report this as a DMM policy before communicating to schedule the radio command to the radio driver. After some time, it will then change its application state to a different state. For example, it's changed here from going to do transmission into going to reception. It's once again going to report that it has changed its application state to the DMM policy table before once again reporting to the radio driver to schedule a radio command. On the DMM side, you have the DMM schedule working with the TI radio driver to figure out which radio command should be scheduled and at what time, since there's only one radio that we are operating from. The DMM creates a scheduling hook that asks several different questions. It's going to be asking, what is the current application state? What is the current stack state? Because you have both application and stack states that need to be interoperating. And is the DMM acting in a balanced or blocked mode? Based on the priorities and the information provided by the DMM policy manager, it once again sends an execution hook and through the DMM scheduler that at execution time, when the TI radio driver is ready to communicate over the air, it will know which stack has the priority and should be allowed to communicate at that time. So let's put this all together. In the end, you have the two application stacks, application stack A and stack B. And you also have stack activity from the TI radio driver. This is all being fed into the DMM policy manager, which has inside of it a global priority table and a policy table. And based on the weights that are generated from all this information and the stack states and application states that the DMM module has available to it, it will be creating a final radio command weight, which it is able to then schedule for the radio driver to send communications over the air. So what are the possible outcomes that are available due to this technology? Well, in the first instance, we have Bluetooth Low Energy in an advertisement state. That is its application state. And so at the beginning, we see that there's no overlap and that the Bluetooth Low Energy that's in blue and the WSN node or wireless sensor network node are not overlapping, so there's no need for the DMM to get involved and intervene. However, in this second instance of the first line, we see that WSN node reception is overlapping with Bluetooth in its advertising. So what happens here is because the Bluetooth Low Energy advertisement state is a lower priority than the WSN node reception state, we see that the Bluetooth Low Energy advertisement is aborted in favor of reception of that WSN node packet. Later on, the advertisement is able to continue as instructed, and it does not continue to overlap with WSN node transmission and reception. However, in the second case, we see the Bluetooth Low Energy is now in a connecting or a connected state. It has now been given a higher priority, and such that it takes priority over WSN node reception. So at the beginning, there's no overlap. But this time, when there's overlap between the wireless sensor network node receiving and that connected Bluetooth Low Energy state, we see that the WSN ACK, or the acknowledgement or reception, is missed due to the Bluetooth low energy activity. So the packet is later resent again when the Bluetooth low energy commands are done, and afterwards communication on both stacks returns to normal. So here's an example block diagram of what can be achieved when you are enabling DMM for your products. So on the left, we have in the darker gray box a TI 15.4 network. And on the right side, we have in the lighter gray box a Zigbee network. So these networks are able to communicate through a shared Zigbee coordinator switch on the right side and a Zigbee router on the left side. However, the router on this left side is integrated to the TI 15.4 network because it is also a 15.4 sensor. So in this case, the DMM is able to concurrently operate the TI 15.4 stack and the Zigbee stack at the same time to realize two different network devices. At the same time, on the right, in the lighter gray side of things, on the Zigbee network, it has a BLE peripheral, meaning that it is able to be commissioned and controlled by a BLE central smartphone, which is shown in the bottom left-hand corner here in the black box. So the BLE central smartphone is able to communicate the switch state to the Zigbee coordinator acting as a switch, which is then able to control this Zigbee router light communicating inside the 15.4 network. Likewise, the BLE smartphone can also directly communicate with other sensors that are inside the TI 15.4 network, because this box on the far left side is also DMM enabled for both BLE and 15.4 stack. So we have in these light blue boxes 3 different instances of how DMM are used with different stack combinations to realize several different forms of applications which can be used in a single ecosystem. So what are the TI devices which are capable of operating dynamic multi-protocol management? Well, in the portfolio here, we can see that there are several devices capable of achieving this functionality. On the left side, we have the 2.4 gigahertz multi-protocol solutions. These are ones capable of concurrently operating Bluetooth Low Energy, Zigbee, Thread, 15.4, or the upcoming CHIP/Matter protocols. Currently, TI offers the 2652R, which is a device capable of reaching up to 5 dBm transmission output power, the 2652P variants, which have an internal power amplifier for reaching 20 dBm transmission powers, and also a 2652RB device, which is the BAW internal wave resonator, so you don't need an external high-frequency crystal to drive your design. All of these are currently available to concurrently operate any of the devices shown, and we also have just recently announced, TI that is, the 2652R and P7 devices. These have increased the internal flash memory to 704 kilobytes and will be reaching production in September 2021. So we're extremely excited to offer these increased flash memory devices so you can further expand on your application and realize exactly what you want your product to achieve. On the multiband side, we have the sub 1 and 2.4 gigahertz devices capable of driving at both of these frequency bands. And so the R and P are exactly similar to what I just described. We have currently the 1352 R and P devices, which are similar to the 2652R, except they can also drive sub 1 gigahertz solutions. There are several examples provided in the SDK for you to get started with multi-protocol management solutions. So on the left side, we have stack combinations that are available with the BLE peripheral application. These include the TI 15.4 stack collector and sensor, the EasyLink wireless sensor network node, and Zigbee roles as coordinator, router, or end device. These applications are available as nodes for both the 15.4 and EasyLink stacks, and then switch and light devices for Zigbee. There are several variants available as well. For example, 15.4 has sub 1 and 2.4 gigahertz options, and all of the options shown include over-the-air download capabilities, which basically means using the stacks to download a new application into your device and not have to have a wired connection or JTAG to be able to upgrade your functionality. All of these examples are available in our SimpleLink CC13X2 26X2 SDK, or software development kit, and all documentation and the examples that I've just covered can be further explored in the TI Resource Explorer available on our website. Also available on TI Resource Explorer is the SimpleLink Academy. What this is are easy walkthrough modules which help get you started with the solutions that TI offers. So for the DMM, this includes DMM Fundamentals, which is a simple walkthrough of an SDK example and covers the basic DMM concepts and features that are available. In the customizing use case, we go one step further, showing how to modify that same example to fit a new use case or something that isn't currently available through the examples by default. Then inside DMM integration, we show how to prepare a project to be integrated with the DMM software module. And this basically features adding a proprietary sub 1 gigahertz stack to an existing project and being able to realize how you can already use a project or design that you have at the moment and incorporate DMM into it. For additional resources, you can also look at the DMM User's Guide, which contains the most in-depth documentation that TI has to offer at the moment for the dynamic multi-protocol management, both its features, its use cases, and next steps. There are also the example READMEs, which have detailed information regarding the application setup and usage, the ins and outs of how the examples are intended to operate. And we also have dev.ti.com/TIREX, which is TI Resource Explorer, to gain the full information about all the resources, documentations, and use case examples that are available to our customers. For more information on TI's offerings of multi-protocol devices, please visit www.ti.com/multiprotocol. Thanks again for your interest in this subject and for listening to me for the past few minutes. And once again, thank you, Rich, for hosting me today. Passing it back to you.
Thank you, Ryan. That was an outstanding presentation. And we'd also like to thank Texas Instruments for sponsoring this event. And of course, we can never do any of these types of things without you, the engineer. A quick note that all Open Systems Media webcasts are copyrighted and may not be recorded without prior permission. So thank you all for attending, and I hope you have a great day.